Hello and welcome to the channel. I'll be showing you a brief overview of how to use Multisim, and we'll take you through a transient and a frequency response analysis, introductory of course. So the first thing that you notice when you open Multisim is that it automatically opens a new page, and this is where you'll be doing your designs. Right, over here you've got different component libraries that you can go. These are your sources, basic components, diodes, transistors, etc, etc. Now to place a component is easy. You can either go there, click there, component, and say you want to find a battery or a DC source, or click on DC source. It's under sources, and you click on OK, click on the screen to paste it. Or if you want something else, say you want to find a resistor, you can still find it using that route, or you can just click there and you'll see that it has gone to the basic library. You get different types of groups. We'll go to basic to find resistor, click on resistors to find resistor, and there we go, we've got a resistor. So if we then want to find an ammeter to measure the current through that resistor, you'll find that in indicators and ammeter, you have a choice of whether you want the terminals to be vertical or horizontal. I want them horizontal in this case, so I'll click on ammeter H and click once on the screen to place it. Right, let's structure this in a more legible manner. So to construct this simple circuit, I'm just going to put the ammeter in series with this resistor and connect that resistor to the source. And the next thing we want to do is to get a ground node. A circuit will not simulate without a ground node. Multisim needs to know where the reference is, and you're telling it that by pressing a ground. Right, if we wanted to measure voltage, we could get a voltmeter in the same manner that we got the ammeter. So we click on the components, go to indicators and voltmeter, vertical. Why did I go vertical? I should have gone horizontal. And the other way that we can do it is to get a multimeter and just place the multimeter over here and connect it across. But when you use a multimeter, you need to be careful and make sure that you've selected volts for voltmeter. If you want to use it as an ammeter, you have to select amps, and make sure that you're either on DC or on AC. In this case we're using DC, so we'll be on DC. Right, so we'll click there to run the simulation, and you should see the current that's flowing across through the circuit there. There's 0.12 amps, and the volt drop across that resistor, since it's just one resistor, as 12 volts, which is equivalent to the supply voltage. Right, so that's a basic overview of how to find components on Multisim, and you can do as many combinations as you want. If you wanted to add another resistor here, you can copy this one, Control C, Control V to paste, Control R to rotate, and you can copy this one again, Control C, Control V to paste, and there you already have two resistors. Let's drag this down a little. No, let's remove you. Right, connect that over there. I don't know why I dragged this window down. Push that up again, and we'll connect this over there. This goes there, and that goes there. Now the volt drop across this resistor should be different, and so the total current should be different as well. The circuit is not grounded. I've removed the ground node, so we need to place the ground node again, and there we go. Right, if we play the circuit now, we're getting 8 volts across this resistor, and the total current is now 8 milliamps. So you can feel free to play around with it, get as many configurations as you want. Right, the next thing I want to discuss is capacitor charge and discharge curves. Right, So I'm gonna hook up a simple circuit to charge and discharge a capacitor using a DC source for obvious reasons. Those reasons aren't obvious, perhaps you should watch a different video. No? Okay, doesn't matter. Right, so that'll be the charging resistor, and then the next thing we'll look for is a single port double throw switch. We find that in the basic group. Then we look for switch and we look for SPDT right there. Right, so you can rotate that to whatever you desire. I would like it to be in this orientation. Then we'll place the actual capacitor that we're trying to charge, Control R to rotate, and a bleeding resistor as well would suffice. So this is the discharging resistor. It's called a bleeding resistor for some reason, because it bleeds the energy from the capacitor, I guess. Right, so I'm simply going to connect this up, and we will observe the charging and discharge curves. I'm first going to do it manually, then I'll do it automatically and give rationale for both cases. Right, so what I'm going to do now is place an oscilloscope across the capacitor, because I want to see the voltage curves as it charges and discharges. Right, and the other thing I'm going to do is just see here. We'll do the times and divisions later on. Right, so when the switch is in this position, the position it's in now, circuit, this capacitor charges through R1. When we flip the switch to this position, capacitor discharges through R2. Pretty simple. The charging time constant is RC, but it takes 5 charging time constants for the capacitor to fully charge. So if we can change this to say 10 kilo ohm, and we multiply that 10 kilo ohm by this, we'll see that it's actually 0.01, I think. My math is a bit stale. Yeah, 0.01 seconds for the charging time. But in order for it to for the charging constant, or the RC constant, and the charging time will be 5 times that, so it's 0.05 or 15 milliseconds if you want to be technical. Same applies here. Change that to 20 kilo ohms, and you can do the math in a similar manner. I will not embarrass myself any further by doing the math again. Right, it is midnight actually, so you can expect a bit of brain lag or brain fog. See, it's happening already. Right, so I've connected the ground node, and what I'm going to do now is pull up this oscilloscope. Hopefully the circuit will be visible. Yeah, and let's bring this baby up. Maybe reduce the screen a little. Okay, technology doesn't want to cooperate. So press the play button, and actually no, let's start it in this position. So let's pull this up. We're gonna start this from scratch again. Right, so let's start the simulation when it's in this position. So in this position, the capacitor is fully discharged. This capacitor is fully discharged and it's not connected to the supply, so basically no current flows. But the minute I flip the switch, the capacitor should start charging, and there you go. As you can see, it's charging. So what I'm going to do is increase this time per division so we can get a better view of the charging curve. Right about there, it has reached a plateau, indicating that the capacitor is fully charged. So what I'm going to do now is flip the switch so that the capacitor discharges, and there goes the discharging transient, and you'll see that it'll asymptote 0. It'll be more of an asymptote towards 0, and at that point you'll know that the capacitor has fully discharged. Right, so makes sense, right? but it would be nice if there was a way to fully automate this process without actually flipping the switch yourself and without this bulky oscilloscope over here. So is there a way of doing that? And the answer is yes. But before we can jump to that, let's get a few preliminaries out the way. So I'm going to hook up a simple circuit with a DC source and a single pole double throw switch, but one that is voltage control. So you get that on the switches, but you go to voltage control as PDT. Right, and we can get a step voltage. So that's under sources, signal voltages and step voltage. Voila. Right, control R to rotate, and you can place that. Then the next thing I want to get is an LED. Let's get green because I like the color green. It's sort of my favorite color, don't judge. And blue. We can place that over there. Right, so if we connect that there, just bear with me, I'll explain the madness behind this in a minute. And we connect that there, and the last thing we need to get is ground. This circuit is mainly meant to be a demonstration of the voltage controlled single pole double throw switch and how to use it with a step voltage or a pulse voltage or whatever you want to use it with. I'm going to use it with a step voltage in this case. So right, we put that there, and we can copy that ground and ground this over here. Okay, how this circuit works is when the switch is in position 1, the green LED should go on. When it's in position 2, the blue LED should go on. But how do we do that? How do we change the state of the switch? So in order to change the state of the switch, you would have to come to the parameters. So you double click on the switch itself and you get to the parameters. We want it to be in position 1 when it says 0 volts across these terminals. So position 1 on state should be 0, and when it says 5 volts across the terminals, we want it to then switch to position 2. So position 2 on state should be 5 volts, and that's all. Right, then the step voltage will determine how long it'll stay in position 1 before it switches to position 2. So I want it to stay in position 1 for 500 milliseconds, so I'll change that to 500 milliseconds. My final level here has to be the same parameter that I chose as the triggering voltage for that switch. That's 5 volts. Right, so I'm going to start the circuit. When the circuit starts, we should see the green LED go on, and then later on the blue LED should go on. So let's run it, and green is on, and when the switch gets triggered, we'll see blue go on, and there we go. And that's all there is to it. This is how the single pole double throw switch works in an automated circuit, so to speak. It just makes this process so much easier. So I've gone on and I've actually done a circuit to help do a transient analysis. I hope I've got the right circuit here. I've got so many saved, it's not even funny. Right, bear with me, I use a very old PC. There we go. Right, so in this circuit we have the same single pole double throw switch over here, a step voltage source, bunch of resistors. This is your charging resistor, and this is your discharging resistor, a voltage source. And these little dots over here are called on-page connectors. What these do is they allow me to connect this step voltage source to this single pole double throw switch without actually making a physical connection. So it's actually the same as taking this, putting it here and connecting it there. How you use them is that the label on this on-page connector has to match to what you want to connect it to. So this is a plus, and that plus matches this one. So in essence, I've connected this component's terminal to there. and this one is labeled GND. So I've connected this GND to there, and that's all there is to it. It's exactly the same as taking this, putting it here, and connecting it with a bunch of wires. It just looks neater this way. So in order for us to run this transient analysis now without these oscilloscopes and whatnot, and to get a much better representation of what we're looking at, we'll click on simulate, we go on analysis, we do a transient analysis. Right, the start time we want to start at 0, but we want it to stop. This is very important, the stopping criterion. When you define the stopping criterion, you have to consider both the charging and the discharging times. So your stopping time should be at least the sum of your charging and discharging times. Meaning if your RC constant times 5 for charging is 1 second, and your RC constant times 5 for the discharging is 1 second, then your stopping time should be 2 seconds. Now I've already stipulated that the stopping time here should be 0.015 seconds. Right. Then the next thing you want to do is specify your output. Right. Now I've already labeled the nets here, but in the event that your nets are not labeled, what you want to do is, let me just get out of this page, is click on the net. This is the net whose voltage we're trying to measure. We want to measure the voltage across the capacitor with reference to the ground. Right, so we're measuring this voltage. Oh god, what have I done now? Right, so you double click on it and you label the net. Now I've already labeled it here VC1, so I won't do that again. Okay, so that when you go to simulate, analysis, and transient analysis, output, you'll find it easily. I've already edited here, but let me remove it so you can see. You'll find it easily on the list of variables. So you click on that variable, click on add, and you simulate. So this is your charging transient, and that's your discharging transient. Right about here, this is where it reaches the supply voltage somewhere here, depending on whether you're on the 5% or the 2% criterion or whatever the case may be. But this is your charging time, and this is your discharging, rather charging curve, and this is your discharging curve. Pretty simple. Right. The next thing I want to show you is how to conduct an AC analysis. Now I'm going to do both an AC, a single frequency analysis, and an actual frequency response. So I've already done a circuit here to make things quick. And no, it's not this one. Why am I opening the wrong circuits all of a sudden? Right. Pardon the background noise, my neighbors are making a lot of noise. Right. So what's happening here is we just have an AC source with a bunch of resistors and a capacitor connected. And what I'm going to do is I'm actually going to measure the impedance, or plot the impedance and the phase. So I'll plot the magnitude plot and the phase plot of the impedance. Now there is no direct way of measuring impedance in Multisim. So how we do that is we use a mathematical expression. In order for you to get the impedance, Ohm's law dictates that the impedance is basically V over I, or the total voltage over the total current in this case, because we want the total impedance. So the total current that flows through this circuit will be the current that flows through R2 plus the current that flows through R1. So ZT, the total impedance, will be total voltage divided by the total current. I hope that makes sense. Right, so how we do this is, if we say we want to evaluate this circuit at 5 kilohertz, even though I've specified that the source is 40 kilohertz here, there's reason for that, we'll come back to it, but I want to evaluate what the impedance is at 5 kilohertz. So what I'm going to do is go to simulate, analysis, single frequency analysis, because I want to evaluate the impedance at one frequency only. Right, I specify the frequency where I want to conduct the analysis, then I click on output. Right, now let me remove everything here so that I can do this expression from scratch. Now we did say that in order to get the impedance, we need to consider the supply voltage Vs divided by the total current. So that is a mathematical expression. To add a mathematical expression, you click on add expression and you put in your variables Vs, copy the variable to expression, divided by, that's a slash, you can put in a bracket using your keyboard as well, divided by IR1, copy to the expression, plus you can use your keyboard for that, or you can come over here to get your functions, IR2, copy to expression, bracket off. And that's it. The expression we want has been added. So all that's left for us to do right now is to run a simulation, and it tells you that at this frequency the magnitude of the impedance is 45.38764. The angle is negative 15.82, whatever nonsense that is, and we expect this to be as follows because it's a capacitive circuit. Right, pretty simple. But now, how do we do a Bode plot, or how do we do a multi-frequency plot or a frequency response plot? So in order to do a frequency response plot of this circuit, which will give us your low frequency response and your high frequency response, or those who are familiar with filters, this will be very handy. So what you do is you go to simulate analysis, and then you find your AC analysis. You're not doing a single frequency this time, you're just doing a general AC analysis. Then if you want to do a logarithmic plot, you'll click on decade, you change that to decade, and the vertical scale, maybe we can change that to decade as well, or you can leave it in linear, it's up to you. I'm going to change it to decade because this is usually what they use. But now be careful, when you change this to decade, you can't have a 0 here because the log of 0 is undefined. So we'll start at 1, and we want it to stop, that is f stop, at 40 kilohertz. The output that we want is the impedance. If you want to get the voltage, you can select whatever you want to get there. But in this case, I just want to get an impedance plot. I want to plot the phase and the magnitude. So I've already written the expression from the previous simulation that we did. So I'm just going to click simulate, and there we go. That's your magnitude plot, and that is your phase plot. And that brings an end to today's presentation. If you have questions, please post them in the description. I will answer them when I have time. And like and subscribe. Thank you and goodbye.